Hello everyone. My talk today is titled with experimental investigation of drug reduction over superhydrophobic surfaces in an open channel flows by Ahmed Alsharief, Ziridwan Bafurnana, and Yuri Muzeshka from Faculty of Engineering and Applied Science, Memorial University of Newfoundland, Canada. The primary points will be highlighted in this presentation include introduction, objective, experimental setup of the present work, preliminary results, and conclusion. The overall drug internal flow can be classified into three main categories such as: first, pressure from drug, which is an symmetrical pressure field between moving objects upstream and downstream sides, and it can be reduced by creating a streamlined shape. The second category, which is pressure interaction drag, which occur when pressure field is projected on surface topography. Its understanding is limited due to the unpredictable changes in the pressure gradient and the flow vortices. The attraction between the fluid and wall surfaces is known as a skin friction, or shear viscous drag, which forms a significant part of overall drag force, and it has received considerable attention due to the tremendous economic and ecological interests in such flows over the last few decades. The reduction of overall viscous shear drag can be classified in three main techniques as active technique, which is, as example, suction, blowing, and heating, which all of them needs extra energy that rises the cost. The second one, interactive technique, which has limited application, such as polymer additive. And the third one, it will be a passive technique, which depends on changing the wall topology to be an superhydrophobic surface. There is another composite technique, which is hyperbolic synergy effect by polymers and additive and modification surface. But our focus, it will be on the passive technique using superhydrophobic surfaces. Superhydrophobic surface can be classified mainly into structured and unstructured surface. There are many methods to fabricate the superhydrophobic surfaces, as illustrated in this figure. But the coating technique is low cost and easy to apply over large areas compared with other techniques. The superhydrophobic coating results from a combination of the hydrophobicity of the surface material, chemically hydrophobic, and surface topography, physically rough. The superhydrophobic coating becomes available commercially since 2016 and open the doors on a wide range of applications such as self-cleaning, anti-fogging, anti-corrosion, anti-fouling, anti-icing, oil-water separation, and in some medical application, but our focus, it will be on the drag reduction. After applying the superhydrophobic coating on the surface, an air layer will trap between the surface and fluid. This layer will work as a lubricator as the result of the different viscosity. This will reduce the shear stress as the fluid flows over the air and creates slip velocity. Slip length is another parameter used to describe the surface slippage velocity. The slip can be interpreted as the depth into the boundary at which the velocity profile can be extrapolated to zero. The slip velocity is directly proportional to the magnitude of the shear rate experienced by the fluid at the wall, as proposed by Napier's slip model, which says the slip velocity equals slip length times velocity gradient. Most previous experiment work is conducted with different measurement techniques and different operating conditions, showed contrast results from drag enhancement to drag reduction. The measurement performed on specific plane or field of view based on the measured technique over the tested surface. This motivated us since the friction and viscous drag contributed significantly to overall drag and reducing it would increase the system efficiency. Using superhydrophobic surfaces shows the promise of drug reduction, although the inconsistencies from the previous study showed limitation in covering the wall surfaces. The present work focuses on measuring the drug reduction over the wall surface from the leading edge to the trailing edge. Using three fabricated superhydrophobic coating surfaces allow us to study the stability of the achieved drug over the three different superhydrophobic surfaces under similar operating condition. The test surface was fabricated from plexiglass sheet with dimension 250 high, 500 millimeter length, and 25 millimeter thickness, with sharp bleeding and trailing edges as shown in this figure. The test surface is a replaceable surface, and the three superhydrophobic coating were applied on one side by separating technique. In contrary to the previous study, 7 planes at different locations in the stream direction were selected to carry out the measurement in the span direction. All measurements were conducted at the elevation between 55 to 16 millimeters above the channel bottom. The experimental work were performed in rectangular recirculating flume as illustrated in this figure, and the depth of water in the channel considered being 130 millimeter. The test surface is a replaceable, as we mentioned, surface and positioned at the center of the channel and after 900 millimeter from the inlet where the boundary layer is fully developed, and the distance between the test surface and the outer channel surface to be 145 millimeter. The flows were seeded with the particle of silver-coated whole ceramic spheres of 10 millimeters, micrometers diameter to capturing the near wall region details. One operating condition at approaching Reynolds number 34,200 was selected for all tested surface, and the two-dimensional laser Doppler velocimeter has a three-dimensional traverse mechanism for flow field mapping over the test surface in many positions and is adjusted to move for 20 points near the wall with a 1 millimeter step, then 5 millimeter step for the rest of to the half channel with it. Total sample time at each point was selected to be 120 seconds. This period yielded around 1,000 to 3,500 random velocity samples for each velocity component. The surface suitability is characterized by measuring the static contact angle and tilt angle using OCA 15E optical goniometer from data physics. Piece of 130 versus 70 millimeter from the same substrate of material of the test surface were used to perform the measurement at 20 different locations. The FBC, which is presented here by blue line, showed more consistent static contact angle at all locations with an average of 155 degrees, compared with the ultra dry of 147 degrees and FTMW 145 degrees. Also, the minimum tilt angle is for the FBC showed 1.8 degrees and 1.9 for the ultra dry and 2.5 for FTMW surface. The velocity profiles of all locations were fitted from the experimental data and presented here. You can see that FBC 800M has higher profile compared to the smooth surface, which was an uncoated surface. Based on a 95% confidence interval, the uncertainty in the mean velocity and the turbulence intensity were estimated to be plus minus 4%. The ultra dry and FTMW surface showed low velocity, especially in the near wall regions. The velocity profiles couldn't present more details about the stability of the reducing the drag. For this reason, the wall shear stress over the smooth and the three superhydrophobic surfaces calculated based on the friction velocity as presented here. The friction velocity for each surface was calculated using the logarithmic law of the wall. This figure presents the distribution of the wall shear stress over each surface at 7 locations. The FBC 800M showed a stable low shear wall from the leading edge to the trailing edge, while ultra-level dry increasing gradually to be higher than the smooth surface at the last location. And FTMW showed low shear wall stress in the first half, significantly increased after the center. This performance can be evaluated by the drag reduction ratio calculated from this equation. From this comparison, we can see that the FBC has a stable drag reduction with an average ratio of 18%, while ultra-level dry and FTMW showed drag enhancement in the second half of the surface, but they produced average drag reduction of 8 and 11% respectively. To sum up, since there is no change in the operating condition for all tested surfaces, the contrast of the drag reduction over the three tested surfaces refers to the inconsistency of the surface weighting degree, especially for the ultra-level dry and FTMW. The FBC 800M showed a high static contact angle and low tilt angle showed a high average drag reduction and stable performance to reduce the drag, and that is clear from the weighting degree measurement. More investigation and data analysis are needed to understand the superhydrophobic surfaces performance and the slip velocity achieved over them. Financial support from Memorial University of Newfoundland and the National Science and Engineering Research Council of Canada, also Libyan Ministry of Higher Education, is greatly appreciated. Thanks for attention and question.